Welcome back, everyone. In this video, we're going to talk more about light, and specifically, we're going to talk about how light also behaves as a particle. So in the previous video, we talked about how light behaved as a wave, and the best example of that was how it gets diffracted, and we have areas of constructive interference and areas of destructive interference. We're also going to talk about in this video about how light behaves as a particle. And this brings up a really weird thing, and that is that how can something be both a particle and a wave at the same time? Well, let me give you a little bit of history here. So in the late 1600s, Isaac Newton, who it turns out is my 10th cousin, one time removed. So he and I share a common ancestor. It's like my great 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 grandfather was his dad. So or his grandfather, or something like that. Really cool. Anyways, so in the late 1600s, about 1680s, late 1680s, Newton came up with what are called the laws of motion. And these laws of motion, there are three of them. They accurately describe the physics of what happens with large objects. You take a ball and you throw it. You push on a car. You drop a rock into water, etc. All of these different things, his laws of motions described how they behave and why. And up until the early 1900s, that was great. And it worked perfectly for everything that we had to deal with. However, in the late 1800s and the early 1900s, scientists started learning about the atom, and that it's really tiny, really small, and that it turns out that it doesn't behave the way that we would expect all the time. And there's the fact that it can behave both as a wave, or light, for example, can behave both as a wave and as a particle. And not only does light behave this way, but it turns out that all matter can behave this way. And we'll learn more about that in Chapter 2. So suffice it to say, it gets a little weird once we start looking at what we call the quantum level. When we look at quantum mechanics or quantum physics, the world that is so small that you cannot see it. In fact, you can't even see it with microscopes. And so it takes a little bit of a leap of faith to understand, to go with some of the stuff that we're going to talk about. But it turns out that all of the science that has been done since the early 1900s has corroborated these ideas. So let's begin. So light is a particle. Max Planck in the early 1900s proposed a theory involving what's called black body radiation. And black body radiation, despite its name, is essentially dealing with the idea that if you heat up an object, the hotter the object is, the smaller the wavelength, or the higher the frequency it will emit. And classical physics, without going into the details, essentially predicted that there would be an exponential increase. And that not only that, but essentially you would get normal light bulbs would be emitting off ultraviolet rays and X-rays and gamma rays, and they would irradiate the entire Earth. The human body should be glowing, according to the classical theory of physics applied to black body radiation. But I don't know if you've looked at yourself in the mirror recently, but you don't glow. You don't glow like a light bulb. And so there's this conundrum, and they called it the UV catastrophe, the ultraviolet catastrophe. There's this idea that our bodies should be giving off light. Things that are heated up should be giving off enough energy to melt the Earth, but that's not what they observed. And so early 1900s, Max Planck proposed that there's actually a discrete amount of energy that is related to light. It comes in these packets called quanta, and this is where the idea of quantum physics comes from. He said essentially that the energy of light is related to its frequency, but that there is a very specific amount of light. This n here relates to the number of photons. And so he said, essentially, for a given number of photons, the amount of energy that is related to it is dependent upon its frequency, and that it's a very specific, quantifiable amount. Later, Einstein, he won the Nobel Prize not for relativity initially, but what is called the photoelectric effect. Early 1900s, he did some studies where he shone light on metal surfaces, and he knocked off electrons from these surfaces. And what he saw was the same idea of what happens when you shine, or if you were to throw a bowling ball at a brick wall. It's going to knock off some of the particles, but only if it has enough energy to do so. And so what Einstein saw is that the light, when it had enough energy, it would eject these electrons. But until it had that energy, nothing would happen. So you could shine light onto this metal and nothing's going to happen. If you increase the frequency of the light, then eventually you're going to get the electrons that are jumping off. It didn't matter whether the light was dim or whether the light was bright in either scenario. The only thing that mattered was the energy of that light, which is related to the frequency of light. So again, the intensity, the brightness of that light doesn't matter. You could shine very dim light onto the metal surface. As long as it has enough energy, it's going to knock off those electrons. And so this further confirmed the idea that light behaves as a particle. Okay? So, summarizing what we saw from the last video, as the wavelength of light increases, its frequency decreases. We saw that this is related to the speed of light. We also saw just now that as frequency increases, that photon energy increases. That's thanks to Max Planck and his idea that light is quantized. It comes in specific amounts of energy. That's it. That's what you need to understand. In the end, this page is what you need to come away with from the idea of light being a wave and light being a particle, is that because it's a wave, we can relate its wavelength and its frequency through the speed of light, and that because it behaves as a particle, we can relate its frequency to the amount of energy that it contains. All right, let's try a couple problems. I'm going to walk you through this one. If you want to try it on your own first, you can pause the video now and then come back. Welcome back. So here's our solution here. We have a green laser pointer. We want to know what's the energy of that light. Let's say you have one photon of that light. One amount of light, how much energy does that contain? So how we do this is by applying the relationships between wavelength and frequency and energy and frequency. Why? Well, we want to know what's the energy, right? In order to know the energy, we need to know the number of photons, which we have, 1. We need to know Planck's constant, which we have. It's given on your data sheet. And you need to know the frequency. That we don't have. In order to find the frequency, however, you can use this relationship, knowing that light is a wave, and relate the wavelength to the frequency. So, to do that, we can rearrange this equation, solving instead for frequency. We plug in our values for the speed of light and for the wavelength, converted, of course, to meters, and then solve. This gets us an answer, a frequency in units of inverse seconds or hertz. To find the energy, we can plug that frequency in and solve. We have one photon using Planck's constant, and then multiplying by the frequency, we have a total of 3.74 10 to the minus 19 joules. Okay, so that is basic combination of energy and wavelength of light. Let's try one that's a little bit harder. Pause the video now, try this one on your own, and then come back and I'll walk you through it. All right, welcome back. Here's the solution. So we have some black light, which you might see if you go to, I like to go to the laser tag type places, do laser tag, and there's going to be black lights. They emit light in the 364 range, so that's going to be UV light. How many photons are in a pulse of light if we have a total amount of energy? All right, how do we want to think about this? Well, we know that energy is related to the number of photons and its frequency. We are given wavelength and energy. So we need to convert from wavelength to frequency. We need to use the energy and then solve for the number of photons. Okay, so to do that, you're going to first take your wavelength and convert that from nanometers to meters. Then take your energy, convert that from millijoules to joules. These conversions are necessary such that all of the units will cancel when we do the calculation. Then we can take and use the wavelength that we've just solved for and solve for frequency. That's going to use the speed of light and the wavelength, and that gets us 8.24 times 10 to the 14 inverse seconds. That's our frequency. To find the number of photons, we'll take this relationship and rearrange it to solve for n, the number of photons. We then plug in our value for energy, for Planck's constant, and for frequency. And then we can solve here to find the number of photons. If I asked you to find the number of moles of photons, what would you do? Remember, to find the number of moles of something, you need to use Avogadro's number. Avogadro's number relates the actual number of something to the number of moles. So if we have 5.29 10 to the 14 photons, and we want to find out how many moles we have, we need to put the number of photons here. And for a mole, that is 6.022 times 10 to the 23 photons. Now, I did not actually do this calculation, so I will leave that to you to figure out, but that's how we would set that up. Okay? Thanks for watching, everyone. Have a great day.